Welcome to this next video in the playlist on ring theory. In this video, what we're going to introduce is the concept of polynomial rings in several variables. Okay, so by now, we are very familiar with the concept of a polynomial ring in a single variable where the coefficients are from some other ring, which we call the coefficient ring. What we're going to study in this video is how to take polynomial rings in several variables. Okay, now to introduce this, we will just start off by looking at polynomials in two variables, polynomial rings in two indeterminates rather than arbitrarily many. Okay, and then we'll study polynomials of two variables, and then we'll generalize this to the higher number of variable cases. Okay, but I hope that just looking at polynomial rings in two variables will give us good intuition about polynomials in several variables. Okay, right, so let's begin. So firstly, let's start off with the notation. How do we denote a polynomial ring in two indeterminates over another ring, capital R? Okay, well, it's denoted just like the ring of polynomials in a single variable, except that you'll have two variables now. So we have R and then square brackets, and then you put x, comma, y, like so. So this would be called the polynomial ring in two indeterminates, in the indeterminate x and in the indeterminate y, where the coefficients are from the ring capital R. Okay, so that's the full name for this structure here. Now, how is it defined? Well, the absolutely brilliant thing about polynomial rings in several variables is that they are defined using what we've already learned about polynomial rings in a single variable. Okay, so the way that we define this is you take the polynomial ring in the indeterminate y, where the coefficients are from the polynomial ring in the indeterminate x over the coefficient ring capital R. So the way this is defined is you take the polynomial ring where you use as the coefficient ring the polynomial ring in the indeterminate x. So it's defined like so, and I'll put bigger square brackets here. So you're taking polynomials in y where the coefficients are going to be polynomials in x, where their coefficients are in the ring capital R. That's the way that we define rings of polynomials in two indeterminates. And then if you wanted to do it in 3 or 4 or 5 or 6 or arbitrarily many indeterminates, you just continue this process on. So in 3 indeterminates, you'd say, okay, create me the ring of polynomials in, let's say, another variable z, where the coefficients are going to be from the ring of polynomials in the two variables x and y. Okay, and then so on. You can just continue on, okay, inductively. So the definition of these polynomial rings in several variables is done inductively with the definition of a polynomial ring in a single variable. Okay, right, so let me make this more concrete. Let me actually show you what I mean by this and give you an example so that we get used to thinking about this. And then what we'll do is we'll talk about the fact that people don't usually write polynomials in two variables in this way. Usually we change the symbols slightly, only a minor change and a very intuitive change, but it is still a change that I need to stress is a change. And then we need to understand how addition and multiplication is going to work in this ring of polynomials in two variables. Okay, right, so let me start off by writing this out explicitly then. Okay, so this is going to be the set containing all polynomials where the coefficients are now going to be in the ring of polynomials in the indeterminate x over the coefficient ring capital R. Okay, so it's going to look like this. It will be the sum over I of AI, and now the indeterminate we're using here is y, so I'll have y to the I here. Okay, and these AIs, these will now be elements of the ring of polynomials in the indeterminate x over the coefficient ring capital R. So these are polynomials themselves. Now, of course, only a finite number of these AIs will be non-zero, okay, because we're doing algebra, not analysis, so we're going to assume that only a finite number of the coefficients are going to be non-zero and the rest are just going to be zero. Okay, right. But that's the big change here, that the coefficients are now in a polynomial ring, and that's perfectly valid to do because this is a ring. So you can take the ring of polynomials over that ring where you're using this as the coefficient ring. Okay, and that's perfectly well defined. Okay, and we know how that's going to work from our study of rings of polynomials in a single variable, but what we're going to spend the rest of this video understanding is, how that works in a bit more detail and how we can change the symbols slightly into the more conventional way of writing polynomials in two variables. Okay, so writing this out even more explicitly then, okay, let's give these AIs, let's write them out as actual polynomials in the indeterminate x over the ring capital R. Okay, so I'll now write each AI as the sum, let's say, over j of coefficients bij, so I need a double indexed structure now. Okay, and then it will be x to the j here. So the I varies with this I here, and the j will obviously be summed over here, and only a finite number of the bij's for each I will be non-zero. Okay, again, because we're studying algebra and not analysis. Okay, right, so there is my explicit expression for AI, so this means that I can now stick this in here, and what I'll get is that the structures in this set will be of the form the sum over I, and then the coefficient for each power of y will be the sum over j of bij x to the j here, and all of that will be in front of yi. And now what I can say is that these bij's are elements of the ring capital R. Okay, so there explicitly is what the things in this polynomial ring in two indeterminates are going to look like. Okay, right, so before we go any further, let me give you a concrete example. Let's take a concrete coefficient ring and let me give you some examples. And then we'll talk about how people often change the symbols. Instead of writing them in this way, we imagine distributing out these brackets, okay? Although that is an imagined thing to do, okay? At the moment, it's not intuitively obvious that that is something that would work to do, but we're going to show that it's something that makes this structure very, very nice to work with, and we can imagine addition and multiplication working with these new symbols very nicely. Okay, right, so firstly let me just give you a concrete example. So let's now look at the ring of polynomials in two indeterminates over the coefficient ring of the integers, a very nice ring that we are very familiar with. Okay, so remember, this is the ring of polynomials in the indeterminate y, where the coefficients are going to be from the ring of polynomials in the indeterminate x, where the coefficients are in the integers. Okay, so let's write out an example of this then. So the constant term, let's start off with the constant term. Well, the constant term will be a polynomial in the indeterminate x with coefficients in the integers. So let's just make one up. What about having 1 plus x squared? That's certainly a polynomial in the ring of polynomials in the indeterminate x over the integers. Okay, so that will be our constant term here. And then let's have the y to the power of 1 term, and again what we'll need as its coefficient is a polynomial in the ring of polynomials in the indeterminate x over the integers. So let's make something up. Let's have 9 plus, what else can we have, negative 2x, and I'm just making this up. As long as the coefficients are in the integers, it's absolutely fine. Plus, what should we go for, 97 x squared. Let's go a little bit higher, so plus, let's say we miss out the x to the power of 3 and x to the power of 4 terms, and we'll jump up to 5x to the power of 5 there. Okay, so there's a polynomial in the ring of polynomials in the indeterminate x over the integers, and now that's going to be our coefficient in front of the y to the power of 1 term, and then we'll go on. So let's say it's just going to be degree 2 in y. Okay, so we'll go up to y squared, so now I need a coefficient in front of y squared, and this is again going to be some polynomial in the ring of polynomials in the indeterminate x over the integers. So let's put something in here. So let's have 6 plus 5x plus, let's go adventurous, 87x to the 77. There we go. Okay, and then we'll have that in front of y squared. And that's a perfectly valid member of this ring of polynomials in two variables x and y over the integers. Okay, so all the coefficients are here. This is a coefficient, this is a coefficient, and this is a coefficient, and they are all in the ring of polynomials in the indeterminate x over the integers. Okay, so that's what I mean by saying that the way you do this is by taking polynomials in y, where the coefficients are from the ring of polynomials in the indeterminate x over the integers. Okay, right, so there's an example, a concrete example. Now let's have a look at the way that we usually denote polynomials in two variables. This is not the way that you usually write polynomials in two variables. You can do it in this way. This is the most formal way to do it. However, very intuitively we change the symbols. So what you can imagine doing now is changing all of these symbols slightly, and the way that you do it is you just imagine multiplying out this bracket. Now I want to stress that although it seems intuitive that you can do that, it is not intuitive that you can do that. Okay, it's a lie. Okay, because these additions here, these are just symbols. Remember the formal definition of a ring of polynomials. Okay, everything is incredibly formal. You just have coefficients from the coefficient ring, which in this case is the ring of polynomials over the initial ring, and we'll go back to having a general ring rather than the integers. So over the general ring R in the indeterminate x. Okay, you just put the coefficients in front of the powers of y. The powers of y are just placeholders. Okay, when you put them in front of there, that doesn't mean multiplication. It just means you've put it in front of there. It's just a symbol. The pluses that you put in between the different terms, those are just symbols to separate the terms. This is the formal definition of a polynomial, that you're just creating these symbols where you put coefficients from your coefficient ring here in front of powers of y and separate them by these symbols, which we call plus. Okay, so it's not intuitively obvious at all then that you can distribute this out, and even, you know, in the ring of polynomials in the indeterminate x over the ring capital R, the pluses here are just symbolic pluses. The powers of x's are just placeholders. Okay, and you've just stuck coefficients in front of all the powers of x's from your ring capital R. So everything's just abstract symbols, so it's not obvious at all that you can expand the brackets in the intuitive way. Okay, however, that's what we're going to do. We are indeed going to expand the brackets in the intuitive way, and that's the way that we more normally write polynomials in two variables. And our job now is to understand how, if we're going to change the symbols in this way, how should addition and multiplication work with these new symbols using how we know addition and multiplication will work in here. And we do know how addition and multiplication must work in here, because after all it is defined just as a ring of polynomials in a single indeterminate where the coefficient ring is a ring of polynomials itself. Okay, so we do know how addition and multiplication is going to work in here. Our job now will be to understand how that translates into our new set of symbols. Okay, so let me firstly do this abstractly, and then I'll show you what this concrete example would become with the new symbols. Okay, so the way we're going to do it is we can imagine a relabeling map, and I'll be terribly formal here and actually give the relabeling map a name. Okay, so we're going to call this map phi, which is going to be this relabeling map, and it's going to take every polynomial in here and it's going to change the symbol. It's a change of symbol map. Okay, it's the map that I'm defining now to change the symbols. Okay, and it's going to be a very small change in symbols. So this polynomial here is just now going to go on to the sum over I, the sum over j, and remember these sums are very abstract sums. They're just effectively describing how you create the symbols. They're telling you to put pluses in between the terms, okay? But they're not real pluses. They're just, at the moment they're not real pluses. They're just symbolic pluses, okay? And then we'll have now bij, x to the j, y to the I. Okay, so I'm now making the terms a power of x and a power of y with a coefficient from the ring capital R in. And now the polynomial is going to become just a series of these terms, which are powers of x's next to powers of y's, okay, with a coefficient from the ring capital R in front of them. Okay, and then you'll have them all separated by a great big plus, which is what these, by those pluses, which is what these sigma symbols are telling you to do here. Okay, so understand how this is different from this. Okay, I've got rid of the brackets effectively, I've expanded the brackets, I've imagined that I can expand the brackets. So let's now have a look at what my relabeling map would do to this concrete example here. Okay, right, so I'm just going to basically expand the brackets. So this bit will become just 1 plus x squared Okay, and now I'd expand this one here, so I'd get plus 9y plus negative 2xy plus 97x squared y plus 5x to the 5y, and then expand this one, then we'd have plus 6y squared plus 5, and I'll just move this up a little bit, 5xy squared, and then we've got plus 87x to the 77y squared. So you see now that all of the terms here separated by all of these symbolic pluses. Okay, so these are just pluses that you put in between the separate terms here. They don't actually yet mean real addition. Okay, this is just this sigma I, sigma j. It just means separate all the terms by plus symbols. Okay, and they're separating these terms which have a coefficient from the ring capital R, in this case the integers, and then they also have the monomial, which is now, a monomial is now a power of x and a power of y. So in my ring of polynomials and two indeterminates, monomials are now going to be a power of x multiplied by a power of y. Now, of course, your power of x could be x to the power of 0, or your power of y could be y to the power of 0. Obviously, in this monomial here, the power of y is y to the 0, and in this monomial here, the power of x is x to the 0, and in here, it's x and y are to the power of 0. Okay, so you've got all of these monomials with coefficients from the ring, the coefficient ring, in front of them, and that's the more normal way that we think of rings of polynomials. Okay, but remember, the way that we define it is as the ring of polynomials in a single indeterminate where the coefficient ring is itself a ring of polynomials. Okay, so it's not trivial that we've gone from that to this. Okay, it did require a change of symbols. And what our job now is to do is to understand how we should add together polynomials that look like this, in terms of how we know that we can have polynomials over here, okay, and also multiplication. So we want to understand how addition and multiplication is going to work in these, and it is going to be incredibly intuitive, and we're going to do it from here, basically. And the fact that it's going to end up being incredibly intuitive here is why it's such a good idea to change the symbols to this. Okay, but do understand that we have fundamentally said, let's change the symbols at some point, and that this mapping is there, and it shouldn't be ignored that it's there. Okay, right. What we're now going to do then is understand addition and multiplication. So firstly, let's just recall how addition should work in here. Okay, and then we'll try and understand how addition should work in terms of our new symbols, which is what we really want to do, because we don't want to have to use symbols like this. We want to be able to use symbols like this. Okay, right. So let's take two polynomials then, that are in my ring of polynomials in two indeterminates. Add them together in the way that we know they should add, viewing the ring of polynomials in two indeterminates as a ring of polynomials in a single indeterminate, where the coefficient ring is a ring of polynomials itself. And then let's translate that understanding into these new symbols that we've got here. Okay, so firstly, just to come up with two polynomials then. So we've got our polynomial, the sum over I, the sum over j, okay, and at the moment it's still in the old sense. aij, so I'll change my symbols now, and then we'll have x to the j, y to the I. So here's one of these polynomials that's in my ring of polynomials in two indeterminates, viewed in the original symbolic form. Okay, so we've got the brackets there, so it's a polynomial in y where the coefficients are polynomials in x. Okay, and then let's add it now to another polynomial, which will be the sum over I, and then the coefficients will be the sum over j, and now we'll have bij, x to the j here, and then obviously it's in front of y to the power of I here. So here is my second polynomial in the ring of polynomials in two indeterminates. And this addition here, this now means addition in the ring of polynomials in two indeterminates. Okay, so in the indeterminate x and y. Okay, so I'll colour code the addition in here. So this is addition here. Now it's a good idea to colour code additions in here, because we're going to see three different additions. We're going to see addition in the ring of polynomials in two indeterminates. We're going to see addition in the ring of polynomials in a single indeterminate over x, and I'll colour code that in purple. And we're going to see addition in the actual ring capital R. Okay, and we'll colour code that in red. Okay, right, so let's get on with this. So how is this going to work? Well, by definition, how do you add two polynomials together, remember this ring of polynomials in two indeterminates, this is defined to be the ring of polynomials in the indeterminate y, where the coefficients are these rings of these polynomials in the indeterminate x. So you just add the coefficients together in the coefficient ring, which in this case is our ring of polynomials in the indeterminate x over the ring capital R. Okay, so this will just become the sum over I, and then you're going to add the coefficients together, so you'll get the sum over j, aij, x to the j, plus, and now this addition is in this ring of polynomials in the indeterminate x over the ring capital R, so I'll colour that in purple, okay, plus the sum over j, bij, x to the j, like so, and all of that's in front of y to the I here, so I'll just move this up a little bit. Okay, so I hope you understand what we've done. We've said, okay, the way we add polynomials is we just add the coefficients. The coefficients in this case are polynomials themselves, so we just need to add those polynomials together in the ring of polynomials in the indeterminate x over the ring capital R. Now all we have to do is ask, well, how do we add two polynomials together in the ring of polynomials in the indeterminate x over the ring capital R? Well, of course, we do it component-wise again. Okay, so let's develop this even further. So this is going to be equal to the sum over I. Okay, that bit doesn't change. And now how do we add these? Well, we just add these coefficients component-wise in the ring capital R. So this becomes the sum over j, and then we'll have aij plus bij. Okay, and that addition is now in the ring capital R, the coefficient ring rather than the coefficient thing. The coefficient ring for the ring of polynomials in the indeterminate x. Okay, and then we'll have that in front of x to the j here, and all of that will still be in front of y to the I. So here is your answer. Okay, so that's how addition works in the ring of polynomials in the indeterminates x and y, using the actual definition of the ring of polynomials in the indeterminates x and y as a ring of polynomials in the indeterminate x, where the coefficients are from the ring of polynomials in the indeterminate x, where we view the definition as the ring of polynomials in the indeterminate y, where the coefficients are in the ring of polynomials in the indeterminate x. It's a mouthful. Right. Okay, what we want to now understand is what does that mean in terms of our other symbols that we can have for these. So what are the other symbols that we could come up with for these two polynomials? Okay, so let me just stress, this is the answer to what these two added together are equal to. What we're now trying to do is understand what this means in terms of adding two polynomials where they've got the other symbols. Okay, so if I apply phi to this, then this becomes the sum over I, the sum over j of these monomials, which are now aij, x to the j, y to the I here. So this is this given its new symbol, the symbol that we prefer. Okay, so here is it in the new symbol. And similarly, let's do it for this one over here. Okay, so if we apply phi to this, what we'll end up with is the sum over I, the sum over j, bij, x to the I, oh, not x to the I, x to the j, y to the I there. Okay, so there's that one in its new form. Now, what we want to know is if we want to add these together, how should it work? What should we end up with in the new symbols? Well, of course, to add them together, what we should imagine doing is returning them back to this, working it out through here, okay, which is the way it's defined, and then transferring this into its new symbol. So let's transfer this into its new symbol if we've got enough space here. Okay, its new symbol, well, just following the law, what we just have to do is multiply out this bracket. So what we'll end up with is the sum over I, the sum over j, okay, and then we'll end up with aij plus bij, where the addition is done in the ring capital R, and I'm sorry this is a little bit squashed into this corner, and then we just have it in front of x to the power of j, y to the power of I, okay? So that's perfectly intuitive, okay? That's just saying, basically, you do it component-wise is what this is saying, okay? Look for terms which have the same monomial, i.e. the same power of x and the same power of y, and then just add the coefficients of the two polynomials in front of that same monomial together in the ring capital R, and then that's the new coefficient that you'll get in front of that monomial in this final polynomial here. Okay, so that then tells us how to add two polynomials together if we are viewing our polynomials with this new symbol. Okay, so if we have these two polynomials represented with their new symbols, the nicer symbols, the symbols we prefer, all we have to do is add together the coefficients that are in front of the same monomials in these polynomials together in the coefficient ring capital R. So that's absolutely lovely. Right, so I think we'll have a break there, and in the next video what we'll do is a similar thing for multiplication. We'll try and understand how multiplication is going to work in this ring of polynomials in two indeterminates, where we're viewing again the symbols as being represented in this form. Okay, and in the break you can be thinking for yourself how this is going to work, and the big clue to understanding how this is going to work is that once you have defined addition, you can decompose polynomials in two indeterminates into a monomial decomposition, where the monomials are now powers of x multiplied by powers of y. Okay, and then if you define multiplication of monomials, there's only one way that polynomials can then multiply. Okay, so we'll do that in the next video.